Another term you need to know about functions is one-to-one function, which means that not only is there only one y for every x, there's only one x for every y, which means that that like two different x's don't give me the same y output. For example, a parabola, if you have a parabola, just standard x squared parabola, y equals x squared. If I put in 2 for x, I get out 4, right? When x equals 2, y equals 4. What happens when I put in negative 2? I also get 4. All right. So this means that this one is not a one-to-one function because two different x's give me the same y. Like if I put in this kind of bread and this kind of bread, I get out the same type of toast. So this one's not a one-to-one function because it shares some y values. And basically the way to do this to find whether this is a one-to-one function is to see if it passes the horizontal line test. So is there any place on this graph where there are two y values from or one y value from two different x values? Does that make sense? So if it can hit two different x values with just one y, not a one-to-one function. And the reason one-to-one functions are important is because they help us find out if functions have inverses. So an inverse function, remember, is when we switch the x and the y and then we solve for y. And basically, it's like we're switching the input and the output. So we, instead of putting in bread and getting out toast, we're putting in toast and getting out bread. And so we're just trying to figure out if a function is one-to-one, then it has an inverse. If it's not one-to-one, it doesn't have an inverse at all, period, done, that's it. So if it fails the horizontal line test, it doesn't have an inverse. So let's look at our examples. It says which of the examples has an inverse. So I just went ahead and drew them. So let's look at the first one. Does this one pass the horizontal line test? Yep, absolutely. There's nowhere on this function that if I drew a horizontal line, it would actually touch two y's. So this one actually does have an inverse. Check. All right, the second one, not only does it fail the horizontal line test, but it is not a function. It asks which is a function with an inverse function. Well, this wasn't a function to begin with, so it fails from the beginning, but it also fails the horizontal line test. So that one definitely does not have an inverse. Now let's look at this one. We just looked at the parabola, remember, and we can see that it fails the horizontal line test. There are two different x's that I could put into this function to get out one y value. So this one is also does not have an inverse function. And then the last one, you might think, oh yeah, this one passes the horizontal line test because it does. But let's reread our question. It has to be a function with an inverse function. Is this a function? Nope. So this one is not a function either. Now we need to find the inverse of this function. And this is an algebraic inverse, right? So remember, the first thing we do is we switch the input and the output. So here's our y equals 2x cubed minus 1. So we switch the x and the y. So now we have x equals 2y cubed minus 1. And then we need to solve it for y, right? Because we need to get x all by itself. So we're going to add 1 to both sides, and we end up with 2y cubed equals x plus 1. I just switched them to the other side, but really I just added 1 to both sides, okay? Divide by 2. So I have y cubed equals x plus 1 over 2. And now to get rid of the cube, I can take the cube root. So I could have the cube root of x plus 1 over 2, or you could have written this, remember, x plus 1 over 2 to the 1/3, because that means the same thing. So here's our inverse. That's it. We would write it as y inverse x equals, and then we could write the actual inverse function. So there you go. And this one is a function because the cube root doesn't have two options, right? Remember, the square root has two options. When I take the square root, it has the positive option or the negative option. Cube root doesn't have that, right? The cube root only has the positive option if it was positive to begin with, or the negative option if it was negative to begin with. So this one only has one option, so it does have an inverse function. All right, piecewise functions. We did these in the Desmos project last year. And just remember that a piecewise function just says, hey, I have a few different functions here that I want to look at, but I only want to see each of them in a certain place. Like I only want to see this is a line, and I only want to see it when x is less than 0. This is a different line, and I only want to see that line when x is in between 0 and 1. And this is a parabola, but I only want to see the parabola when x is greater than 1. So I only want to see each of these in certain places. So this is the piece that belongs to the line, this is the other line, and then this is the parabola. So piecewise functions are not that scary, I hope. So we're going to graph the piecewise function and then give the domain and range. So the first thing that I can do is I can graph both of these and then just erase the parts that I don't want. Or what I could do is I could cover up the part that I don't want to look at, and then I could just graph the rest. Okay, so like, so this first one is an absolute value of x. We know the parent function of the absolute value of x is this V shape. Right, just looks just like that, except for, it actually goes through the right points. Okay, there we go. It's this V shape, but we only want to see this when x is less than 1. Right, so I'm going to go over this. I actually only want to see it when x is less than 1. So right up here to 1. I want to see it there, but then I don't want to see it anymore. So it's kind of challenging on here to like erase there we go. Woo. On yours, it might be a little easier with just a pencil. You could just erase what you didn't want, right? Or what I could have done is I could have said, I'm just going to cover up all of this area and I'm going to graph this function, and then I'm just going to stop when I get to that covered up area. So that's another option. All right, and then it says I want to see the other function x plus 2 when x is greater than or equal to 1. Well, what does x plus 2 look like? Well, x plus 2 is a line with a slope of 1 that goes through the intercept of 2. So it has a slope of 1. So here's the line. And I'm not going to draw the rest of the way down because I know I'm just going to have to erase it, right? But I only want to see this when x is greater than or equal to 1. So I'm going to put a solid dot right here because when x is equal to 1, I want to see this function, but not when it's greater than 1, or not when it's less than 1, sorry. So I want to see that line when x is greater than or equal to 1. So make sure you just think about your closed and open circles there. So we're looking at our domain. What values are legal to put in here? Well, there's nothing illegal about this, right? There's nothing that like is going to take the square root of a negative number. There's no numbers that are excluded, right? Because right here at 1, sometimes that number will be excluded where you've got this jump discontinuity, but it's not excluded. It says, hey, I don't want it on this function, but I do want it on this function. So every number possible works for this function. So the domain is all real numbers. Okay, and what is the range? Well, let's see. So the lowest possible value I can ever get to is 0. And the highest possible value, let's see. Okay, so here it takes on all these values all the way up to right here, and then it takes on to infinity, both of them. So it goes from 0 to infinity, right? The biggest thing is you want to check any jump discontinuities and see, okay, where this discontinuity is, am I missing anything anywhere else? Is there anywhere on the graph where I still have those points? And I still do have all those points right here. So my range, I can write it in 2 ways. So the first way would be interval notation. So I would say from 0 to infinity, and I would include 0 because 0 is part of the domain, or sorry, part of the range, right? Because I can get a 0 out. Or, so that is interval notation. That's the most common one. We could write it in inequality notation where we could say y is greater than or equal to 0. Either one, but like I said, the purple one is definitely the more common one and the one that you see a lot more in higher level math. This one kind of fades into the wayside, and this one is definitely the king after calculus. Okay, so now we're looking for zeros. We're trying to figure out what x values give us a y value of 0, right? So this is where it crosses the x-axis. So we're saying at what x values is y equal to 0? So typically zeros are just going to be written as a single number, but x-intercepts are going to be written as ordered pairs. So if it asks for x-intercepts, you write ordered pairs. If it asks for zeros, you write a number, okay? So with a calculator, we know how to do this. We already did this in the last section with a calculator, but without a calculator, what do? We're looking for the x intercept, right? So we're looking for where y equals 0. So we set this function equal to 0. We say, okay, y is equal to 0, x squared minus 3x minus 4, and then we just have to solve it. So let's factor this one first. So let's see, x minus 4 and x plus 1 would give me negative 3x and negative 4. So it's factored. And then remember that the zero product property tells us that if this whole thing is equal to 0, either this has to equal 0 or this has to equal 0. One of the two has to equal 0. So we say either x minus 4 equals 0 or x plus 1 equals 0. And then we just solve those. So either x equals 4 or x equals negative 1. If I put either one of those numbers into this function, I would get out 0. And you can test it. Go ahead. So negative 1 squared is 1 minus 3 times negative 1. So negative 3 times negative 1 is a positive 3. So we have positive 1 plus 3, which is 4, minus 4, which is 0. And then if we put 4 in, we get 16 minus 12 minus 4, which is also 0. So both of those are zeros. So our zeros of this are those. This is a very, 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 very important skill in calculus, to be able to find zeros, because when we're looking for things, when we're looking for derivatives, and I'll tell you what those are about next chapter, but when we're looking for certain things with derivatives, we absolutely have to be able to find where something is equal to 0. We have to find its zeros without a calculator. If you are struggling, you need to talk to me, and we need to work some more of these, because this is something that you cannot live without in calculus. Okay. Soapbox down. All right, zeros of this one. So where is y equal to 0? So you might be tempted to say, well, where the top is equal to 0 or the bottom is equal to 0. But remember, the bottom can never be equal to 0. Well, for a couple reasons. Nothing squared plus 4 is ever going to equal 0. But the other reason is the bottom can never be equal to 0 because we can't divide by 0. It's against the law, right? So remember, when you have a fraction, we don't care about the bottom at all. Who cares about the bottom? It will never equal 0. What we're trying to find when we're looking for zeros is we're saying, where is the top equal to 0? Because if the top is equal to 0, it doesn't matter what's on the bottom. It could be 0 divided by 1 Google. It's still a 0, right? Because 0 divided by anything is 0. So we're just going to set that equal to 0. And we're going to solve. So x squared equals 4. What number gives us 4 when you square it? You might be tempted to say, oh, well, x equals 2. But there's another one. Remember, when we take the square root of a number, we're going to have x equals plus or minus 2, right? Because we took the square root of something, we have to have that plus or minus. Because if I put positive 2 in here, I'd get 0. And if I put negative 2 in here, I would also get 0. So my zeros are x equals